Hello there, ATS 114 students. Dr. Shragi here, and I'm going to talk to you a little bit today about Lab 8. You notice we're skipping a couple labs right now. We're going to come back to them in a couple weeks. But Lab 8 is the one that comes closest to doing what you're doing right now or recently have finished in the lecture. And, you know, there's a lot of material in the course about atmospheric motion. It's kind of weird that there's just one lab called atmospheric motion. So we're not going to be able to do everything that's in this lab activity. It would take us more than one lab session to get through the whole thing. We're going to kind of focus on the forces that are at work in the atmosphere and how they affect the winds at the surface, just to kind of have a single thing that we're addressing in this particular lab, a kind of a single focus. Now, if you remember from your lecture, there's 5 main forces that are affecting the atmosphere. Pressure gradient force, Coriolis force, centrifugal force, gravity, and friction or viscosity. They're all important. But in my experience, the bottom 3 there, centrifugal force, gravity, and friction, students don't really have a hard time understanding those. It isn't necessarily all that worth our time to have a lab activity about centrifugal force. I think you understand the centrifugal force. So let's spend some time on those other 2 forces to make sure that those concepts are something that you do understand. Now, the pressure gradient force is a force that is acting on air parcels, and it is pushing them from high pressure to low pressure. You know, like for example, in an aerosol can, you have relatively high pressure inside of a spray paint can. When you release that pressure by opening up the valve, the air is accelerated from higher pressure to lower pressure. Well, obviously a lot of features of the atmosphere feature high and low pressure, and there will always be a force pushing the air parcels from an area of higher pressure towards an area of lower pressure. And as kind of a little case study to show that, I'm going to show you these kind of old weather maps from November of 1940. This is actually an extremely famous storm. This is the Armistice Day storm. Almost 200 people in America died, mostly duck hunters, astonishingly, who went out to hunt on this day. And because it was a holiday, they had the day off, they went out and went duck hunting, and they got caught in this storm and died. It was a huge snowstorm across the upper Midwest. Anyways, this is a weather map here, and the contour lines that are on this map are isobars. They are lines of constant pressure, and those lines of constant pressure help us understand that, oh, I see there's a big area of low pressure, very strong low pressure, 975 millibars, centered over, what is it, roughly Wisconsin at that time. And just for comparison, there's an area of high pressure behind it over Montana. And we can kind of start getting a sense of what the weather pattern looked like on the Armistice Day storm. A gradient, you notice the word gradient is in the term pressure gradient force. A gradient is how a property changes over a distance. In this case, we're talking about the property is pressure, the pressure gradient. So we're talking about like if you drove from one location to another location, over a certain distance, how much did the pressure change? And we can use a weather map like this to kind of get a sense, at least in a qualitative way, of what the gradient is. Like at that yellow spot right there, the isobars are very close together. If you drove across that area where I have that yellow spot, the pressure is changing a lot as you drive from one location to another. We're crossing lots of isobars. So the pressure gradient is large in that location. And in contrast, down there where that green spot is, the pressure gradient is weaker because the isobars are farther apart. If you drove the same distance, you would not encounter as big of a pressure change as you would up there where that yellow spot is. That therefore gives us a sense of where the isobars are close together. We have a strong pressure gradient and therefore a strong pressure gradient force, like the area there where I have circled in red, kind of all across like Minnesota and Wisconsin and so on in this particular example. Whereas places where the isobars are farther apart, well, you have to go a long ways to encounter a change in pressure. There's not much of a pressure gradient, so there isn't much of a pressure gradient force. Now the actual lab activity, much like some of the homework or discussions have in the online section anyway of the lecture, has you actually draw some examples of the vectors that represent the pressure gradient force. Which way is that force pushing air? Doesn't mean the air is going to move that way, because there's always other forces at work as well, but at least which way is that force pushing? And when you draw these pressure gradient force vectors, you always want to draw them perpendicular to the isobars. Okay? And you want them to be directed in a way so that they are pushing from higher towards lower pressure, and draw them longer the stronger the pressure gradient force should be. In other words, the closer the isobars are together, make your vectors longer. So like if I just sort of sketched in here at my yellow location and my green location what I would want the pressure gradient force vectors to be, notice at both locations I had those vectors oriented from higher pressure towards lower pressure, perpendicular to the contours locally, and the vector is longer where the isobars are closer together, the vector is shorter where the isobars are farther apart. Notice I have the vector starting at the location that I am talking about and then pointing in the direction of that force. Okay, so you'll be doing something similar to that. This is another example of a figure that does such a thing that I use actually in my lecture. Where here I happen to have a big area of high pressure over the North Atlantic, and you can see how there's places where the pressure gradient force is strong because the isobars are close together, and there are places where the pressure gradient force is weak and the isobars are far apart, and you can see by the length of the vector how strong I mean the pressure gradient force to be. The other force I want to spend a little time on today is Coriolis Force. Nothing frightens an ATS instructor more than to have to talk about the Coriolis Force. It is a very complicated subject, and we try to just narrow this down to the handful of most important things that you need to know about the Coriolis Force. I mean, for example, we have already talked and heard in the lectures about how the Coriolis Force can only serve to deflect motions. The Coriolis Force cannot accelerate a motion or slow motions down or anything like that. We've talked in the lecture about the fact that the Coriolis Force is due to the fact that the Earth is round and rotating, and it's very difficult to get a handle as to why that would be. Even in upper division and graduate level Coriolis Force, atmospheric science courses rather, getting a handle on the Coriolis Force can be really tricky. I mean, the students don't have trouble remembering things, that Coriolis Force deflects all motions to the right in the northern hemisphere, it deflects all motions to the left in the southern hemisphere, and so on. We draw the Coriolis Force vector on a plot. If you know the motion, you draw it as a vector 90 degrees to the right of that motion to show that it's deflecting the motion that way. But getting a handle as to why that is really, really hard. On the other hand, there's a couple of online videos that are just spectacular examples of this. It turns out you don't need to be, the Coriolis Force on the Earth is relatively weak and slow. It deflects winds that blow across a cyclone and an anticyclone because they're in motion for days and days. But you can demonstrate the Coriolis Force in a really neat way using a merry-go-round. See these kids on this merry-go-round? They are rolling a ball. Now the merry-go-round is rotating a whole lot faster than the Earth is. Its angular velocity is a lot faster than the Earth. And from the point of view of an observer above or off of the merry-go-round, the ball is moving in a straight line. Okay? But from the point of view of the kids that are on the merry-go-round, the ball is deflecting. Now, as it happens, this particular video comes from a school in Australia, so the video shows it deflecting to the left, okay, because it's the southern hemisphere. They were trying to demonstrate that. But see, the ball goes in a straight line. If you're off the merry-go-round, to your point of view, it looks like it's moving in a straight line. From the point of view of the kids on the merry-go-round, the ball is being deflected. I love this video. Many props to this guy who figured out how to do this and demonstrated this for this video. Now, how are we going to demonstrate this in your lab activity? The lab activity has you working on one of the pages with these two little circles here. It may not be immediately clear. I don't know why they didn't put like a map on these circles, but you're looking down on the top panel there. You're looking down on the globe, like looking at the North Pole, and on the bottom panel you are looking up at the globe, towards the South Pole. And what they want you to do is to actually put your paper on the desk and set some kind of object in front of you. Like I'm going to put a little smiley face there. And what they want you to do is to work with a partner and turn your little lab manual here, but well, first draw a line that just shows from the North Pole straight towards your little object, okay? Just to show that's what a straight path looks like. Now, what they want you to do is, with the help of your partner, they want you to slowly turn your book in the direction of those arrows. But don't turn like based on the middle of the book. Turning with the axis being like at that spot that's the North Pole. Try to use this little example that I'm doing here with this animation to help you. Just gently turning the book as, around an axis there at that North Pole. Okay, not the middle of the book, but the middle of that graph right there. And as you're doing that, start with your pencil at the North Pole and slowly pull your pencil towards that object that you put out in front of your book there. As the book is turning, you're just slowly pulling your pencil towards that face that's on there or whatever, and you'll get that kind of nifty curved line. Okay? As the paper turned under, your pencil moved in a straight line, but the path that it followed on the paper is curved. Just like those kids on the merry-go-round, how as they rolled the ball across the merry-go-round, the ball was moving in a straight line, but from their point of view on the merry-go-round, it was a curve. Notice which way the ball is curving here, or your pencil is curving. From the point of view of moving forward, it's curving to the right in the northern hemisphere. You're going to do the same sort of thing on the second panel there, turning it the right way for the southern hemisphere, and you should get a deflection to the left. You're going to do the same sort of idea using an analogy of, they actually in this printing of the book are saying a rocket launched or a missile launched at from the North Pole straight south. And you're going to do that, for example, on pages 86 and 87, and they could have done so much to make these figures more clear. There's 4 figures right there, but 3 of them are giving you information, and they are time 1, time 2, and time 3, like I have it sketched on there. And you can barely see on their diagrams, they're trying to show you 3 different positions of the rocket at different times. So I've kind of highlighted there, it's like this end of this little arrow or whatever that's on that diagram, so I highlighted it with these red dots. You can see that the rocket has been moving from time 1 to time 2 to time 3. Another thing they could have made a whole lot more clear here is notice that there is that map on the background there, and it's rotating. See how at time 1 where North America is kind of at, what would that be, something like 7 o'clock on a map, on a clock, and then on time 2, North America is at about 6 o'clock on a clock, and then at time 3, North America is at like 5 o'clock. See how the North America is turning? Okay, what they want you to do is actually put your answer on that last panel, where they want you to transfer the locations of the rocket at the 3 times onto that map. And if you follow very carefully and look, oh, I see I'm on this latitude, I'm on this longitude, I see, okay, great, you'll get a kind of a little curved path, okay? It's a little hard to draw that in PowerPoint, but you'll get a little curved path showing that the rocket is deflecting to the right. You're going to go through a series of those kinds of activities, actually, for a rocket fired from the southern hemisphere. They're going to make you do one where the rocket's moving faster, another one where the rocket's moving slower, and you're going to be figuring out things like how the speed of the rocket influences the Coriolis force. Okay. We're going to apply these ideas of these different forces to winds at the surface. And one of the questions that you're going to be answering involves this figure 816, and boy, I am not at all happy with how unclear figure 816 is. Let me point to a lot of things they should have told you about this figure 816 so that you won't be so stressed about this figure. First off, it's not at all clear on this diagram here, 816, that this is part of a map. Okay, like you can kind of think of it as like, you know, put some states on here if it'll help you or something like that. This is a map. Okay, it's just a piece of a map, but it's just a piece of a weather map there. And in fact, it's a map of pressure. Those 2 lines there that are labeled 1012 and 1016 millibars are isobars. They are part of a much larger weather map with lower pressure to the north of this map and higher pressure to the right, to the south of this map. I don't know why they don't tell you that in the question, but that would make it a whole lot easier to understand what's going on. Another thing they don't tell you is what is this little square that they drew on here? That square is supposed to be like an air parcel. It's a little volume of air that is just sort of sitting, where you can move it around, etc. That's supposed to be an air parcel. And then we're going to be wondering what this arrow is. That arrow is supposed, that vector on there is supposed to be the current motion of that air parcel. It's moving that way. Then, okay, if they just had told you all of that, that makes the instructions then a whole lot more clear. Basically what they say is, now draw and label the 3 forces that we've been interested in, pressure gradient force and Coriolis force and friction. Okay, friction we didn't spend any time on. Students generally understand friction is slowing the air down. You draw friction as a vector pointing the opposite direction of the motion. So you're just going to sketch on here 3 little vectors. A pressure gradient force that's pointing perpendicular to the contours from high pressure to low pressure. You're going to draw a Coriolis force vector. I believe in this example you're supposed to be in the northern hemisphere, so just draw a vector 90 degrees to the right of the wind, and draw a friction vector the opposite direction of the wind. That's all there is to it. It's a minute of work if they had just told you what all those things mean on that diagram. So, alright, and then you do the same sort of thing for some locations on a series of weather maps where they aren't telling you if this is an area of high pressure or if this is an area of low pressure. And it's an interesting activity. It's worth the work. What you'll notice is that at the surface, the winds are not quite parallel to isobars. Remember, today we're not talking about winds aloft. Winds aloft, the winds are parallel to the isobars. At the surface, they're not quite parallel to the isobars, but they are kind of in the same general direction, and they will keep the wind to the left of the flow in the, they're going to keep the wind so that low pressure is to its left in the northern hemisphere, and then southern hemisphere will work the other way. Low pressure will be to the right of the flow. If you've been following along closely in your readings, you know that that is the curiously named Bisbelot law. Bisbelot was a Belgian scientist who discovered this idea that the wind should be blowing in such a way that low pressure is to your left in the northern hemisphere. Alright, you should also be finding that the winds at the surface are crossing the isobars a little bit from areas of high pressure towards areas of low pressure. And that's actually going to be really useful to understand what's going on with cyclones and anticyclones. If I go back to this map from the Armistice Day storm with this giant cyclone centered on Wisconsin, well, we have all these little wind symbols on in these station models on the plot. Those little wind symbols there are those little feathered shafts that are called wind barbs. The only part you need to know for this activity is that the shafts are pointing upwind. So you see all those little wind barb symbols at all those different stations right there? If I just sort of traced with my colored pen on my PowerPoint here, you see that they make winds around the cyclone that do something characteristic. The winds, this cyclone is always, whether they're in the northern hemisphere or in the southern hemisphere, a cyclone is an area of low pressure. And whether they're in the southern hemisphere or whether they're in the northern hemisphere, cyclones have convergence. Air is converging and spiraling in towards the middle at the surface. They are different, though, as to whether it's in the northern hemisphere or whether it's in the southern hemisphere as to which way the winds go. In the northern hemisphere, the winds around the mid-latitude cyclone go counterclockwise, where they're going to be clockwise in the southern hemisphere. In contrast, let me take a different day. This is from the European Weather Archives, just for a change of pace. And we have a big area of high pressure centered over Scandinavia at this time. And again, there's wind barbs on there. They're probably pretty small on this view. You probably can't see them, but I traced some of them, kind of made a streamline of the flow. And you can see that the flow around the anticyclone does a curious thing. Anticyclones are always going to be areas of high pressure, and they are always going to have divergence at the surface. Winds are spiraling out of them as winds cross isobars from higher pressure towards lower pressure. Anticyclones always have this rotation around them where the winds are rotating clockwise in the northern hemisphere. It'll be counterclockwise in the southern hemisphere. This is going to set up weather patterns. Areas of low-level convergence, like we see in a cyclone, result in rising motions. If you haven't already seen that in your version of the lecture, rising motions are always associated with clouds and precipitation and so on. That's why areas of low pressure are associated with stormy weather. Anticyclones with their high pressure and low-level divergence are always associated with sinking motion from the upper atmosphere, upper troposphere anyway, as air sinks back down towards the surface to replace that air that diverged. Sinking motions are always associated with clear skies and fair weather. Alright, I think you have everything in hand now to take on Lab 8. You'll notice that we're skipping a lot of Lab 8. I don't know how many weeks they would think it would take to finish this lab. Alright, but we'll do it, just parts of it, and we'll just do it in one. Alright, great. I wish you the best of luck on this lab activity, and I look forward to talking to you next week.